So as part of US EPA's Construction General Permit and NPDES program, site operators on construction sites are required to implement stormwater pollution prevention plans. So this is an aerial photo of a typical big box store where they've gone into a green field, they've completely cleared and graded it. They're in the grading phase now, and you would have to install stormwater management plans in order to control any stormwater that is flowing on your job site and controlling it on your job site before discharging it off and potentially discharging sediment-laden water. So as part of this site stormwater pollution prevention plan, you're going to have a variety of controls. The first control being a sediment barrier. You may have some inlet protections to prevent stormwater from getting into subsurface conveyance systems that could be discharged into nearby waterways. We're going to have conveyance channels that collect and convey stormwater to a particular point on the site, which typically leads to sediment basins. Sediment basins are generally there to collect detained stormwater for a certain period of time, allow sediment to fall out of suspension, and then discharge cleaner or less turbid water off-site. So we have done a lot of research at the Erosion Sediment Control Testing Facility at Auburn University. It's located on the grounds of the National Center for Asphalt Technology, which is a 1.7 mile oval test track where they do accelerated pavement performance testing. And the erosion control facility occupies about 2.5 acres worth of land on the southeast corner of this particular property. We have 3 primary missions. The first mission is to do research and development, where we work with the DOT or product developers to better understand the product, see whether or not we can identify deficiencies through research, and then try to come up with some pretty practical solutions to improve performance. We also do product evaluation and testing. So if there is a manufacturer that has a product and they want to get on the DOT's product approval list, they will come to Auburn. We can test them and compare that product to some of their non-proprietary practices and make comparisons between the two, and then give some actual research data to the DOT. And then from all this information that we learn through research and development and product evaluation, we try to hold training events. So once a year we hold a pretty large field day where about 100 practitioners come out and they get to gain some of the knowledge that we've learned through research and development and testing. We have 4 or 5 different research apparatuses, and I'm going to show you 3 of these today, and these are just highlighted in orange. We have a rainfall simulator, we have channelized flow experiments that look at ditch checks and inlet protection practices. We have a sediment basin research testing apparatus, and then we also have a surface skimmer tank that we can evaluate dewatering rates of surface skimmers that are used on construction projects. And then we have a whole variety of just stations that we've set up to demonstrate various techniques and technologies during field days and site visits. So the first thing, what I want to talk about today in this particular presentation deals with runoff control practices. So these are the practices a contractor would install on site in order to control and convey stormwater flows. The idea behind it is to reduce flow velocities so we don't erode the channel, and we want to facilitate the settlement of suspended particles maybe upstream of a sediment basin, so we can maintain them a lot easier, and then that sediment basin can act as a polishing tool to get the rest of the sediment that takes a little while to fall out of suspension within the basin itself. So this first project that I want to talk about is just the evaluation of ditch check practices using large-scale testing techniques. So ditch checks, they're also known as check dams, are just small barriers that we would put in a swale or a conveyance channel that's going to receive some form of concentrated flow. And their purpose is really to be an erosion control. A lot of people think they're sediment controls, but their primary purpose is to impound water in such a way where it flattens the gradient within the slope, slowing velocity, slowing shear stresses, thereby not eroding that channel and allowing vegetation to establish in order to hold it intact. Any settlement that falls out of suspension as part of these impoundment pools is a secondary benefit of a ditch check. So what we have out at the test facility is a 40-foot long channel that has a 4-foot bottom and it has 3-to-1 wing walls, so it's a trapezoidal channel. Top width is 13 feet and it's about 1.5 feet in depth. The first 25 feet of the channel is sheet metal, so when we put concentrated flow that goes down the channel, it doesn't erode the head of the channel. And then we have about a 15-foot earthen section where this is our installation zone, where we would install in particular practice, we would evaluate its performance, and then move on from there. So here is what LDOT's old standard installation of a 20-inch wattle would look like. This is just a straw wattle. It's put in a U-shaped format. Flow is flowing from the left to the right. And then they would use wooden stakes. They would pierce the wattle and they would drive the stakes about 18 to 24 inches into the ground, 2 foot on center. So when we tested this, it really didn't perform that well. With the stake piercing the wattle, it allowed the wattle to kind of move up and down and become buoyant, so it would float. Thereby, you wouldn't have good ground contact with the wattle and the channel surface, allowing for a lot of undermining to occur. So it would scour underneath this device. It would not create a very large impoundment, as you can see here. I think the impoundment was only about 10 feet. The ponding depth was about 1.24 feet, but it never overtopped it because it eventually undercut it. So what we wanted to, this is a structural problem. It's a structural deficiency, and we wanted to evaluate it to try to improve it. So we did a little bit of literature. We saw what others were doing. One thing that we picked up from the North Carolina Department of Transportation is they use a TP staking or an A-frame pattern that we applied here, and what this does is it holds the wattle in place, it puts downward pressure on the wattle itself, and it gives better ground contact. We also put down an 8-ounce filter fabric underlay to prevent any kind of erosion or scour underneath a particular practice, and then we put sod staples on the upstream and the downstream face every 10 inches on center, which basically held the wattle down to the ground, and this performed much better. So we actually got an impoundment that was more than 20 feet. It extended upstream into the channel, and you can see down there in the lower right-hand corner, we actually had water overtopping the device, which is what we're trying to get it to do because we're maximizing its impoundment potential. The one thing I like about this picture is you'll hear a lot of wattle manufacturers, doesn't matter what material it's made out of, it says they'll always tell you that their product filters the stormwater. In this picture, if you look at how turbid the water is upstream and how turbid it is downstream, it does very little filtering. So it's really not a filtering mechanism. It's a means to impound water to slow it down and prevent erosion. We also look at it from a structural standpoint. So this is at a higher flow rate. It exceeded the structural capacity of that particular product. And the problem here is when this happens, you're going to release a tremendous amount of water downstream that's going to get other practices to fail, and it could cause more problems on site than you want. So we got to this point where we would only characterize straw wattles for low flow situations, and they shouldn't be allowed in high flow situations. The flow rate that we were using in low flow is about 0.0625 cubic feet per second. Our medium flow is 1.25, and then the highest flow is 1.875. We also looked at your typical riprap installation. So this is a standard class 1 riprap with an 8-ounce filter fabric underlay. This performed okay. It's structurally sound. It's not going to erode underneath it because of the filter fabric, but due to the nature of it being very porous, it only impounded water 14.5 feet. It was fine for the highest flow rate. The riprap never moved. It was good for 1.875 cubic feet per second, but we wanted to see if we can improve this performance even more. So some DOTs require filter stone, where you'll use a number 4 stone or 57 stone on top of it to kind of act as choking means to choke the pore passages. That increases the impoundment maybe a couple of feet, but what we ended up doing is we put a filter fabric overlay over it where we pinned it to the channel, and you can see the overlay here. And this actually worked quite well. The beauty behind this is it'll help you maintain this practice over time, because if you ever got sedimentation to occur on the upstream face of this particular rock check dam, you could basically take that filter fabric off, move it, and then replace it with a new piece of filter fabric. When we ran a test on this, it completely choked out all the pore passages. It did not allow a lot of flow through it. It impounded the stormwater the entire length of the channel, which was about 30 feet, and it allowed for overtopping in a controlled situation, which now it performs exactly the way it's intended to. Here's a sandbag ditch check. So this was at the highest flow rate. It's 3 rows of sandbag on the bottom and the middle row. They're stacked side by side, perpendicular to flow, and then that top row is also perpendicular to flow. But every time we tested this at a higher flow rate, we would have a slippage failure between each of the layers, which would cause that failure and that mass release of water. So what we ended up doing is we rotated the middle row 90 degrees, and then we also added additional sandbags to provide structural support in the flow line of the channel. We ended up using less bags than the original design, and this actually worked great. And this is what a DOT would use on hard bottom channels, and we also used it here in an earthen channel. You see a little bit of erosion in the channel itself, and that can be prevented if you put down a filter fabric underlay. We also looked at silt fence installations. You know, we always heard that silt fence shouldn't be used in concentrated flow areas, but we were able to conduct tests in such a way where we could do this. And then the best part about this is most silt fences are trenched in. This is a trenchless silt fence installation. So on the left-hand side of the screen, basically the silt fence fabric is laid down in a V fashion. We would install the T-post accordingly. We would attach the wire backing, and then we would attach another layer of silt fence and pin it into the ground. So it has a little bit of filter fabric upstream and downstream to act as a splash pad. And then the last thing we did is we cut in a weir in the middle of the silt fence ditch check so that we can control the flow in the middle of the channel and not allow it to go around the edges. So we control where the discharge point is associated with the channel itself. And this is what it looks like when it's operating at the high flow situation. What we ended up doing is we ended up putting a board at our discharge portion of it to create an impoundment. That's what you see in the lower portion of the diagram. And in the ideal situation, John, I think you showed a diagram of this where you would have flow go from an impoundment pool to an impoundment pool if things are spaced correctly depending upon the grade of your channel. And that's what we were trying to illustrate here. And if you can achieve that, you're going to reduce erosion within the channel when it's in its temporary state before vegetation is established. We did a couple longevity tests on this. We did 6 back-to-back tests where we were introducing sediment-laden water. And this was able to capture 90% of the sediment we introduced. And this is probably in the range of 1,600 pounds worth of sediment. The DOT actually adopted this, so this is what an installation would look like out in the field. This is in Centerville, Alabama. This is looking from the upstream end towards the downstream end, and you can see how well this channel was able to achieve vegetation. I turned around and took a picture looking upstream, and they used it consistently within the median. They were able to control flows, control stormwater velocities, and get this median channel vegetated. So it actually worked quite well. So when we look at effective ditch check designs, we notice that if you put an underlay, it prevents any kind of undermining or scour, and it actually increased the performance of the wattle from an impoundment standpoint by 80%. When we looked at the riprap, if we completely choked out the pore passages with that filter fabric overlay, we maximized the impoundment 100%. Just by rotating the middle row of the sandbags and have it be parallel to flow, it minimized that friction resistance, and then we added support bags on the downstream end in order to give it additional support in the flow line, and we were able to increase the flow capacity from the low flow all the way up to a high flow application. And then we've proven that you can install silt fence in a concentrated flow line as long as you have a discharge weir that allows you to control where flow is going to. And that performed adequately, and we have several of those installed on the site that have been out there for years and they've never failed. Not sure what's going on with the color, but that's okay. The next project looked at inlet protection practices. So we looked at a variety of inlet protection practices. Okay, I'll hurry up. So I'll go through this pretty quick. So there's a lot of failure modes associated with inlet protection practices. We have short circuiting. We have flow bypass and restriction. If they're not installed correctly, we're going to see undermining, structural failure, improper installation, which all can have downstream impacts. So this is an example of a wattle installed as an inlet protection practice. It uses 4 20-inch wattles by 10-foot wattles. It's got an 11-foot inside diameter. We have TP staking every 2 feet, 18 inches in depth, and then the wattle overlap connections were at 12 inches, and this did not perform very well. We had a lot of undercutting, undermining. The wattle would become buoyant. It didn't have good ground contact, and it eventually basically just failed. So you can see here, we had a lot of deposition on the inside of the practice when we want to have that on the outside of the practice, and we had a lot of erosion at the head of the channel, and really there was no impoundment. Added a filter fabric underlay. We reduced the diameter to 7 feet, which means we only used 3 wattles. We made the connections 18 inches instead of 12, and then we included sod staples on the inside and the outside of the wattle to hold it down to the ground and give it better ground contact, and we were able to get full impoundment, which allowed for overtopping, and this performed very well, and we were able to retain about 70% of the sediment that we introduced. This is what it looks like after the fact, and you can see there's deposition with no channel erosion. We also looked at silt fences. This is a trenched installation, standard installation where you have wire backing, standard T-post. This is what it would look like fully installed. How do you think this worked? Not very well. So when we tested this, the hydrostatic pressure of the impoundment caused it to fail and cave in, and it just doesn't perform very well. So we looked at improving it. We looked at a lot of different iterations. This is the one that we thought was most feasible, that had a filter fabric underlay, T-post, and then there was cross bracing in order to give it structural support. And then we also did the pinned installation where we didn't trench it. This is what that installation looks like, and we also added a dewatering board to allow it to dewater over a very short period of time once the impoundment formed, and then this is what a time-lapse video of this looks like. So you can see as the water level increases, it'll get to the entire height of the silt fence, which is about 32 inches. It never fails structurally. It eventually overtops. And then here in a second, you'll see what that dewatering board looks like. And it aids as an effective means of dewatering, because if you didn't, this material gets blinded and that water would be in that low-lying area for an extended period of time. So this was a pretty awesome installation. And it was able to retain about 90% of the sediment we introduced. Sandbag installation, 3 rows of sandbags. You can see once we actually put water on it, it created a failure very similar to what we saw in the ditch check application. So we did the same thing as we did in the ditch checks, where we ended up rotating the middle row. So we reduced the diameter. This middle row we rotated 90 degrees. In relation to the other rows of sandbags. We added a filter fabric underlay, and it actually performed outstanding. It maximized the impoundment, dewatered in 120 minutes, and we had about 70% sediment retention. And this is what that looks like. So again, effective installations, making sure they're structurally sound, provide for a means of overtopping, prevent undercutting, and then make sure you have effective means of dewatering so the contractor can get in and continuously do work. The last one, there's only like 2 slides here. It focused on sediment barrier practices that are used as perimeter controls. This is the testing apparatus. It's got kind of the same setup where we introduce water, we put it down a 3-to-1 slope, we get it to spread out as sheet flow using diversion vanes, and then you can see our earthen test section that we have down at the bottom, and then we collect everything in a collection tank, and we just put in a pole barn so we can do things in all weather conditions. This is what the standard LDOT installation looks like. It's 32 inches in height. It's got 10-foot T-post spaced 10 foot on max. on center. It's a 6-inch by 6-inch trench, and then we have C-ring fasteners every 2 feet to hold the fabric to the wire backing, and we use a 0.85 pound per foot T-post. So this didn't work very well once we actually started loading it with sediment-laden flow. This is the third test on a single installation. You'll see that middle T-post will eventually deflect, fail, and then discharge a tremendous amount of water. And we wanted to figure out a way to prevent this from happening on future occurrences. So we went through all sorts of different iterations. So to show you what we ended up coming up with, we had T-posts that were heavier weight. They were, again, we had a 6-inch by 6-inch trench. The T-posts were offset 6 inches instead of in the trench, and we used 1.25 pound per foot T-post in terms of the weight. And then this is what the attachment looks like. We ended up compacting with a mechanized means of compaction, which did a lot better. And then we didn't have any voids around our T-post. If you ever had undercutting, that's where the water would come from. So this ended up being a much better installation, and it performed great. I believe this is, and then the last thing is when you get an impoundment like this, you got to have a means of dewatering. So we eventually, and you don't see any deflection here, we put in a dewatering board. So in low-lying areas where you have concentrated impoundments, this is a very effective way to release the water in a controlled fashion, and it really doesn't affect the amount of sediment that this particular practice retains. And I know I'm over time, Wes, so I will end it with that one. Any questions? I know I hit you guys with a lot of information in a short period of time.
So, are any of those performance, is that documented anywhere?
So there are a variety of reports. If you actually go to our website, which is esc.auburn.edu, you can find all of those historical test reports that we did with Auburn, or the research reports. So the majority of the things that we've shown through testing, they have adopted as their standard practices. So they changed their standard check dam or ditch check installation. They're using the weir and the trenchless silt fence ditch check. They've updated all their inlet protection standard installation methods. So they've adopted quite a bit of it.